Hey everyone.
Hey, here we are, just floating it up into the sky, you know.
Beautiful day out.
Wow, wow, we are really far up here.
Yeah.
Holy God.
I have no idea how to land.
Don't either.
A little worried.
Well, since we're up so high, I figured why not talk about gases?
Why not? Seems
Because-
perfectly natural.
Yeah, exactly. So we're going to start with just a few properties of the gases, okay? So let me just throw these up here, then we'll go through them. Whoa, a little too
kind of
I
excited.
got quick on the trigger. All right, so volume is variable. Well, what does that really mean?
Well, a variable is something that's not constant.
Okay, so
So
there we
we got
are.
that.
Okay, so meaning for gases, a volume can change.
Okay.
Okay, so let's say we have an amount of gas in a syringe, for example.
Mhm.
I can squeeze it. It's the same amount of gas, but it takes up a different amount of volume based on how much I compress the empty space together.
Oh, okay. That makes sense. Sure.
Right?
Yeah.
Okay? It has a very low density. What do you think that kind of...
Okay.
I mean, how would you look at that?
Well,
Low
density is mass per volume.
Okay.
So I'm going to say that a little mass of gas has a huge volume.
Right, and that's because gas has so much space between all their
They're
particles.
so far apart.
Which leads
Hey!
us to the next point, okay? So the molecules are spread super, super far from each other. So it
Okay.
can take up, like we said, a huge area because there is so much space between each
Okay.
particle.
And that's why we can compress it too, right? Because there's all that space that we can push it into.
Exactly.
Perfect.
Okay, gases are fluid. So when you think of a fluid, what do you think?
I think of it like like a river flowing down a hill.
Okay, and I typically think of pourable. I don't, because it pours out of a glass.
Able to be poured.
Able to be poured,
Not
yes.
potable, which is drinkable.
Right.
Pourable.
Pourable.
Gotcha,
Okay,
gotcha.
I'm not sure if that's a real word, but we'll go with it.
Mhm.
Okay, so for example, I think we've done where you've mixed rewind, vinegar and baking soda.
Okay, yep.
And what gas do you produce?
Carbon dioxide.
Perfect. And you can actually put out a candle by pouring the gas,
Oh.
not the liquid, the gas.
So
on top of the
gases can flow.
Right, exactly.
kinda cool.
Okay.
Okay.
And then last but not least, they completely fill their container. And they completely fill their container because they're moving like crazy.
Cray.
And they just have so much empty space. So they take up the whole area.
So they fill the container they're in, and then you can compress that container. You cannot. Okay, got
Mm-hmm. Exactly. Okay. So what this is talking about is what we call the kinetic molecular theory.
it. Yeah.
Okay. So this is a theory based on an ideal gas.
Okay.
So when you think of something ideal, you're thinking of what?
Like the perfect situation, kind of? Or
Right.
the perfect gas?
Mm-hmm.
Okay.
Okay. So in this case, they use the KMT, if we will. Okay.
Yep.
The KMT, and to predict how gases will respond
Okay.
or how they're gonna act.
Okay.
Okay.
In a perfect world.
In a perfect world.
Gotcha.
Yes. Okay. So number one, they are always in constant, rapid, straight line motion.
So a gas particle is just going to go off on its
Correct.
own. Gotcha.
Yes. It's going to travel super, super fast in a straight line until it runs into either itself, well, not itself, another particle, or the wall of the container.
Okay, and then it'll just bounce off of it, right?
Right.
And go in another straight line.
Exactly. So it's like if you took a bouncy ball and you chucked it at a wall. Travels in a straight line until
Gotcha.
bam, and then it goes in a different
Gotcha.
Okay, but it doesn't like zigzag or
No, it
anything,
doesn't
straight.
do it. Okay.
Okay. So there's a lot of space between the gases. We've already talked about that.
Because they're going so fast. Got it.
They collide with each other and they make pressure. So colliding with each other and colliding with a container.
Okay, so pressure is really just gas particles hitting container wall.
Yes.
That's really all it is, right?
Yes,
and
that's
if you have a lot of gas, the pressure goes up
because they're hitting each other and the wall.
Gotcha.
Okay. And then collisions are elastic. What do you think that means?
Well, I think it might mean that no energy is transferred.
Yep. Very
Just
good.
gonna throw it out
Yeah,
there.
perfect. Okay, so they bump into each other and that energy doesn't change, it just goes the opposite direction.
So they are the absolute perfect super ball, right?
Yeah.
They will bounce off a wall
And just keep
forever.
going. Forever. And just keep going.
Wow.
It's pretty awesome.
Pretty
Okay? So we're going to use those when we talk about the different gas laws and how they're acting and those types of things. So there are a few variables that we talk about when we refer to gases.
Okay.
Okay? So first one is temperature.
Okay.
Yeah, that was not all supposed to pop up at the
That's
same time.
a lot. Yeah.
Mhm. Okay? So when we're dealing with gases, most of our temperatures are going to be in degrees Celsius. All
Okay.
right? Which, not bad.
We can do that. That's,
Right.
Doable. Okay.
However, when we get later in the unit and we're talking about gas laws, we need to convert those temperatures from Celsius to what we call a Kelvin.
Okay.
Okay.
So Celsius Kelvin, you just convert between the two.
Mm-hmm.
Not the end of the world. Okay.
Right, and it's a very easy conversion. I've listed it there for you, okay? So 0 degrees Celsius is equal to 273 kelvins. So if you need your Kelvin, you're just going to take your Celsius temperature and add 273.
Easy.
Yes. If you need your Celsius, you take the Kelvin and you subtract 273.
Done.
Okay, so very, very simple. All right, so anytime you do a calculation, you want to make sure you're in kelvins.
Okay.
Okay?
Make sure. Got it.
For example, this question says liquid oxygen boils at a normal pressure at negative 182 degrees Celsius.
Okay.
What is this temperature in Kelvin?
All right. So I take my negative 182.
Yep.
I just add 273,
Correct.
and I get my Kelvin.
Mm-hmm. So 91 kelvins. Very, very simple.
Very, very, very,
Okay?
very simple.
We'll do more practice with those in class, but again, you add or subtract. Very
Yeah.
easy.
Calculator. Boom.
Mm-hmm. Done. Or cell phone. Whatever.
You know, not in their class.
No, not in my class. Okay. The next variable we talked about, so we did temperature. Now we're doing volume.
Whew.
I know.
Thin air up here, huh?
It is. Yeah, I mean, we're just getting woo. We might just see the sun soon. So we're gonna do volume.
Probably already can. It's daytime, right?
It is. So we're doing volume, and volume is dealing with length times width times height. That's like
Oh.
old school 5th grade math right there.
Boom. Yeah. Got it.
Okay. And most of the times you're not gonna have to figure out the volume. It'll just say the volume is. Bleh. Okay.
Okay.
And it'll be in a typical unit of a liter, a milliliter, a cubic meter, or a cubic centimeter.
Okay. And since the gas fills the container it's in, if you know the volume of the container, that's the volume of your gas.
Exactly.
All right. Nice
So,
and easy.
and then we know if it's in a liter or a milliliter that it is typically liquid. If it's a meter cubed or centimeter cubed, we know that it is a.
Gas.
Okay.
Solid.
Yes. Okay. So that's what we're talking about there. Okay. And then I put some basic conversions because sometimes it'll ask. Maybe one unit will be in a milliliter, the other one will be in a cubic centimeter, so you have to convert those back and forth.
I hear
Again,
you.
very simple. It's right there for you. Pretty
That's my
easy.
favorite conversion, by the way.
What?
Cubic centimeters to milliliters.
Really?
Oh, it just feels really nice.
Because it's really
I like it.
easy
Yeah, you
and it's
take.
the same thing.
Yeah, exactly.
Okay. All right.
Unit of length turns into a unit of volume. I
It's
just really like that.
just glorious. Okay. And then the next one we have is pressure. So we did temperature. We did volume.
We're getting
I'm
there.
telling you. And then pressure. Okay. And pressure is just, like we said earlier, the particles hitting the walls of the container.
Mhm.
Okay. So a force over a specific area.
So the force is the particle hitting the container.
Mhm.
The area is the container wall. So
Correct.
okay.
Then we have some units that we use particularly when we're talking about pressure.
There's a lot of them. Huh?
There is. And I think I left one off. So we have atmospheres. We have millimeters of mercury.
Okay, so mmHg is millimeters of mercury.
Right.
Is that mha?
It's not. Pascals or kilopascals is a
Okay.
measurement of pressure, symboled with PA or kPa for
Gotcha.
kilo. You know. Okay.
Gotcha. Okay.
Pounds per square inch is probably the one that everyone is most familiar with.
Sure, like your tires, right?
Right.
Gotta
Yeah.
Check that.
So PSI, and then I left off torr, TORR.
Short
bar.
for Torricelli,
Yeah.
the Italian scientist.
Thank you for that.
You like that?
Yes.
Little nuggets of
Little,
info.
you'd be
Mhm.
great on Jeopardy. Okay, and then bar I also left off too,
Oh,
which
man.
I know. What can I say? I dropped the ball. Again, we'll practice these. There's some easy conversions that go with those.
Yeah,
as
it
well.
looks like a lot, but really it's not that bad.
Right. Okay. And then last but not least is the amount of moles. So this
Ooh,
kicks
mole,
back
mole,
to our good old buddy,
The mole.
the mole.
Avogadro.
Avogadro. Okay. The most attractive scientist there is.
Man.
Okay. All this says is that the same equal volumes of gas. So if I'm dealing with oxygen and chlorine, whatever we're dealing with,
Mhm.
okay, have the same number of molecules or equal number of molecules.
Okay.
Okay. So and it's directly proportional to that number of moles.
Okay, so you're saying like a liter of oxygen has the exact same number of atoms as like a liter of chlorine
Correct.
or what have you.
Correct.
Okay, which is a little bit different because usually that's not always how it is, right?
Right.
Like if you had 1 gram of oxygen, 1 gram of chlorine, it wouldn't. But
Right.
the fact we're dealing with volumes.
Exactly.
Okay.
Well, it's different. And then it's fun. And then last but not least, it says at STP, it tells you exactly the volume. Now, we haven't covered STP. We'll get to that in 1 second. But just know that 22.4 liters is the amount at STP. Okay, and it's considered our molar volume.
Ooh, yeah. We
Okay?
can use that a lot.
Yes, absolutely. Okay, so that brings us to our, there it is. Okay, STP. Okay, that stands for standard temperature and pressure.
Good.
Okay, and so anytime you're doing a problem and it says
Mhm.
at STP, they're not going to give you the temperature, they're not going to give you the pressure.
It's shorthand.
Right,
right?
exactly. So you should just know that the temperature is automatically 0 degrees Celsius.
Or 273 Kelvin.
There you go. And then the pressure is 1 atm.
Okay.
And then, again, like it said last time in the previous slide, that the volume was 22.4 liters.
If you have 1 mole of the gas.
Exactly.
Gotcha.
Okay, so that's what you're going to be using there. We're going to take some practice at some of these in class and do a lab, and we'll catch you later.
All right.
Bye.
Bye.